Hello, I'm Breton, one of our MCAT tutors here at Inspira Advantage, where we help students get accepted into med school and other professional programs. Today, we will be putting into practice what you learned in the last video, oxidation states. Specifically, we want to be able to do this on a compound-by-compound basis, as well as understand oxidation states in the context of oxidation and reduction. The MCAT loves to test the concept of oxidation and reduction by combining it with other subjects, so we will practice that together before you see it on the real test. Let's begin by quickly recapping what we previously learned. By order of priority, we assign a 0 to free atoms. For the first row of the periodic table, sodium, potassium, so forth, we assign a +1 state, and then to the second column, we assign a +2. Hydrogens are going to be a +1, and oxygens are going to be a -2. And then finally, for our lowest priority, we have the halogens at a -1 charge. Now, let's move on to some practice. What I want you to try and practice is filling in these little red squares with the oxidation state that these individual atoms possess in the compounds to the left. Now, take a moment, pause, and try to work on through the first problem. When looking at KMNO4, we first want to figure out what our highest priority group is. In this case, it is that first column. We've got a potassium, so it's got to be potassium as our highest priority. And that's a simple, easy one. There's only one of them, so it's contributing a +1 charge. Now, our second highest priority group is our oxygen over here. Well, we know our oxygen is going to contribute a -2 charge for each oxygen. We've got 4 total, multiplied by 4. So we're contributing an overall -8 charge. And we know that this overall compound has to be at a 0 charge. Well, if we know that the K is bringing a +1, the oxygens are bringing a -8 charge, this leaves us with a total -7 overall. To get to 0 then, Mn must be at a +7 charge. Without it, it simply wouldn't equal 0. So now filling these in, we already figured out Mn. We know our potassium is +1, and we know our oxygen is -2. If you got this, congratulations, nice job. Now let's try H2Fe3O4. Again, pause your video and give it a try yourself. Now, just like last time, the first step we want to do is figure out what our highest priority atom or element is. In this case, it's the hydrogen with a +1 charge. We multiply this by 2 to figure out the overall charge that is being brought by the hydrogen. So we get an overall charge of +2 being contributed. Okay, now again, iron isn't on our list, so oxygen is our next highest priority element. Oxygen, we know, has a charge of -2. Again, we're multiplying by 4, so we get a total of -8. And just like last time, we know that the overall compound is equal to 0. So instead of our 0, we're going to add those 2 positive charge from the hydrogen, subtract the total of 8 from those oxygens, then we're going to get -6. Okay, so based on the logic from last time, well, if we want to have a net 0 charged compound, iron must be contributing a +6 charge. But you might see what's wrong here. Well, we've got 3 irons. We have to figure out how much charge each individual iron is contributing. To do this, we can just do some division. Just take 6 divided by our 3 irons to get the charge being contributed by each iron of 2. So we can plug that into our work up here. We said our hydrogen is +1, our iron is +2, our oxygen is -2. Nice work. Now let's kick it up a notch with something you'd be more likely to see on the MCAT. A reaction asking you to identify what is being oxidized and reduced. Let's start with everyone's favorite glycolytic precursor. Just like last time, write down the individual charge on each atom, But also, I want you to write down which molecule is being reduced and oxidized. Good luck. Okay, for that sugar, we know that H plus is the highest priority, and it's going to contribute an overall charge of plus 12. Next, we have our oxygen, which is going to have a -2 charge and contribute an overall of -12. Okay, nice. So this tells us then that we're already nice and balanced, so carbon is just going to have a charge of 0. Nice. Now, these oxygens, we haven't talked about them a ton yet, but we have mentioned what they are. This is actually an example of those free elements. So it's just going to have a charge of 0. The highest priority on our list of priorities here are those free atoms at 0. That's exactly what elemental oxygen is. All right, so we figured out the reactant side. Now let's look at the product side. Again, we have our hydrogen in the water as our +1. Oxygen's got to be -2. That's going to balance out nice and easily. Now things get weird when we look at our carbon dioxide. So carbon, that's not on our list, so we're not going to worry about it. We're going to focus in on oxygen. Oxygen must have a -2, contributing an overall -4 charge. We only have one carbon, and it needs to balance out to 0, so carbon must be a +4 charge. So what is being reduced? We know that through oil rig, oxidation is loss and reduction is gain, tells us that something should become more negatively charged if it is reduced. So we want to find the molecules that become more negative in the product side. The O2 is going from a charge of 0 to -2. Okay, so the O2 must be being reduced. And it's being reduced, so then the reduced thing would be the H2O. Then because the carbon is going from 0 to +4, aka it is losing 4 electrons, it must be being oxidized. So we'll put our sugar on the being oxidized. And if it's being oxidized, the product must be, well, oxidized, which is just going to be our CO2. Nice work. And if that was tricky for you, don't worry, because you get another shot at it. We'll let you try another one. Now, this looks a little strange, and I just want to draw your attention to, I'm going to give you a +1 charge on the product NAD+. Take your time on this. Pause the video. And give it your best shot. Good luck. The first thing we want to notice is, given the +1 charge of NAD, this saves us a step of having to worry about figuring out its oxidation state, because it's +1. Next, let's focus on what we do know, because this is written in a form you haven't seen before. We know that H+ is super high priority and is going to be +1. So let's just fill that in. So if this is +1, if the overall has to be -1, then we know NAD must be -1 in the reactant side. Now looking at complex 1, this is actually acting as a free atom. I only drew one box here. There's only one element, not really element, but compound we have to worry about here. So this just has a charge of 0. There's nothing fancy going on here. It's just existing, and it doesn't tell us a charge, so we must assume it is uncharged at 0. Now, how about our H with complex 1? Well, we know that hydrogen has a +1 charge, so complex 1 then must have a -1 charge. Okay, so now it's time to use the rules of oil rig to figure out who is being reduced and who is being oxidized. Because the NAD in NADH is going from -1 to +1, we know that it is being oxidized. So we can fill that in. Complex 1, on the flip side, is going from a charge of 0 to a charge of -1. Therefore, it's gaining electrons and being reduced. So we'll put complex 1 right there. And we can fill in the product side. So if our NADH is being oxidized, well, the oxidized form was just NAD+. And then this leaves us with the reduced must be H complex 1. Great work, everyone. Thank you so much for watching our video on guided practice with oxidation states, and I'll see you next time.